Okay, very good morning to all, to the chairperson and also the presenter for this particular meeting and conference. So my name is Norhasri Sidek from UiTM Shah Alam. UiTM stand for University Technology Mara, and currently I'm part under on the Center of Excellence that called as Institute for Infrastructure Engineering and Sustainable Management for UiTM. So the title of my presentation today for this particular meeting and conference is the role of nanometakaolin and nanometaclay in ultra high performance cement piece. Okay. Before I start any further, this is some introduction on the past researcher on the current revolution of concrete, starting from normal, high performance concrete, and also ultra high performance concrete. So basically, maybe members of the floor that in the conference and also in the meeting also have a basic knowledge on the concrete itself. So it's just sharing on what type of a concrete that been used in the construction today. So we can classify concrete into three, which is the first one is normal concrete, which the range is between 20 to 50 MPa. So it's a basic design regarding targeted strength within 50 MPa that we are using on the DOE standards. The amount of cement is locked at between 355 kilogram per meter cube. Okay, so there is no supervisor added, and normally it been do for the building and also structure element for frame and others. So the next application of HPC that we call as high performance concrete, the strength increased from 50 MPa to 100 MPa. So to achieve this strength, we need what we call as supplementary cementitious materials, such as silica fume, fly ash, and others. And again, to have a very good strength, which is more than 50 MPa, we need to add special type of admixture. For example, polycarboxylate, retarder, and also accelerator. Normal fine and coarse grade is needed due to the compactness of that particular concrete, and there is a standard design to achieve this kind of strength, which is either ASTM or ACI, or the most popular design method is by using what we call a Dilarat. Okay, so the issue between normal and high performance concrete, we are talking on the macro and micro structures. Okay, and the latest, not so-called latest, but currently been developed in all over the world is on the application of ultra high performance concrete, which is the strength is more than 100 MPa and can achieve to 200 MPa based on the demand of unique structures in the construction today. So normal practice for UHPC design, they are using silica fume to enhance the strength from more than 100 to 150 MPa. So a new generation of admixture that we call as hyperplasticizer is being adopted, and also to cater on the brittleness of that particular design, they add steel fiber to cater on the tension zone. Again, the issues for UHPC to achieve strength more than 100, the compactness of that particular concrete can be achieved by utilization of silica sand, also quartz. Right, so these are the image that been discussed since 2016 by Professor Soblev from Russia regarding on the pores in concrete from macro, micro, and also nanoparticles. So as you can see, this that been described is in number one. This is what we call as hydration product of hydration gel. For civil engineering practices, we call this as calcium silica hydrate. Okay, so these are the binder formation that influence the strength of that particular concrete, either normal, high performance, or ultra high performance. So basically, the performance and the durability of that particular concrete relies on this particular hydration product, on how it bind from one gel to another gel. Oh, sorry. Okay, right. So during the process of binding, there is what we call as bridging effect, that causing by the reaction of cement from what we call as CaOH2. Okay, so this particular bridging effect is not good for the binding effect in the concrete or the cement paste, due it will create more voids between the binding medium. So the idea now is to fit in this particular number 3, what we call as pores, and depends on the type of the concrete itself, as been explained earlier. In the normal concrete, we are facing the problem on the micropores. For high performance concrete, we are facing on the micropores, and for ultra high performance concrete, we are facing on what we call as nanopores. So the challenge is to fit in the gap between the hydration product to ensure a very good density of that particular concrete, to confirm and to confirm on the performance and the durability of that particular concrete structures, right? So these are the past researchers regarding on the normal concrete itself. So I will go very fast on this. Okay, this one is high performance concrete, and this is the latest on the ultra high performance concrete. Just to share with the audience and on the members of the floor, there is no standard design on the ultra high performance concrete till now. So basically, most of the researcher, in terms of optimization of their mix for UHPC, they are using more on the trial and base method. Okay, so these are the one of the most top researcher that regarding that focusing on the UHPC design. And so the differences between the gap, or the differences between the previous research and mine is my cement content is the lowest among the among other researchers, and the additive for this particular design of UHPC is by using nanomaterials from clay base, and is a water cure, compared to others researchers by using, they are using either heat treatment or autoclave, right? So another differences between my mix compared to the others is the application, uh, the nanomaterial being adopted in this particular design is not being used by other researchers, and I'm neglecting on the using of silica and also fibers, especially on the carbon type of fibers, due to it's not cost effective, especially in Asia. And I can stress out that this particular design for UHPC can be claimed as eco UHPC design. Okay, right. So this is how I optimize the mix for my design based on several trial of methods, and I'm locked on the workability, which can achieve around 150 to 200 mm in terms of slump, and the strength can achieve until 120 MPa at 28 days. So based on these trial methods, the trial number 7 that involve cement 800 kilogram per meter cube, with the addition of hyperplasticizer 16%, 16 kilogram per meter cube, which is 2% of cement weight, and workability and the water of 160 kilogram per meter is the best design to achieve that particular targeted in my objective. Okay, so coming back to the research objective, so basically in this meeting, I will focus on two objectives. So the first one is to characterize the physical and chemical properties of nanokaolin, nanoclay, nanometakaolin, and nanometaclay. And then the second objective to determine the effect of nanometakaolin and nanometaclay inclusion to the physical, chemical properties and microstructure of nanometakaolin and nanometaclay cement piece. Okay. This is the research scope for this particular presentation. Basically, this research has been done for and completed at 2016 and now in the process of applying in the industry. So the first stage I will focus for this particular meeting, I will focus on the stage 1 and stage 2, which focusing on the cement paste instead of concrete. Okay. Right, so this is experimental program. So again, as we stated earlier, I will focus on the stage 1 and stage 2, which is stage 1 is the task on the presenting and producing the nano itself from what we call as ball milling effect. Okay, and stage 2 is by to study to see the performance on the nano material itself in terms of addition and replacement method by using setting time to ensure on the water demand and the performance by using compressive strength. Okay, for stage 1, we are focused on the characterization in terms of the nanoparticle itself based on SRF, which is elementary, SRD on the composition, and SEM on the imaging results. Okay, two methods were applied in this particular study. The first one is as addition, and the second one is as replacement. Okay, so the difference between two type of study is for replacement, the amount of nanomaterial being included in that particular design is to replace the cement itself, and for addition, there is no replacement added, but go for additive, which is again the additive is from the same material, which is nanometakaolin and also nanometaclay. Okay. So these are the mixed proportion to achieve on the water demand on the setting time of that particular cement base. Okay, so this one is for addition method, and this one is for replacement method. So these are the process of producing the nanometakaolin. Okay, so again, the main idea of this particular research is to see the potential of local kaolin in Malaysia to produce what we call what an advanced materials in nanoparticles. Since in Malaysia we have a very lot of quantity of kaolin in Malaysia. So the kaolin, when it reactive, it become metakaolin. So metakaolin is is already known as advanced material in the cement industries. So the potential of that particular kaolin is being changed from micro level to nano level. So to confirm on this particular transformation from micro and nano, we use what we call as high energy milling back in our lab in ISEM. Okay, so there is three type of bar and balls for the milling method, which is steel, alumina, and zirconia. And we also running the trial method based on hours and diameter of the balls. And based on this table, we can see that to achieve the size that we are targeted basically on this particular nano cement paste is 15 numbers of ball of 1 mm, which with the diameter of 10 mm, and hours needed to transform from micro to nano is 24 hours. Okay, the exact size that we managed to reduce is the size of that particular nanokaolin is up to 176 nanometer in size. Okay, right. So for calcination process, since there is no, during the research has been conducted, there is no papers to refer on the effect of nanometakaolin and also nanometaclay, especially in the cement studies. So to confirm on that particular calcination process, so I adopted what we call as trial run method to see on the best hours of temperature, hours and also temperature to achieve the strength at 120 at 28 days. So from that, the best calcination process is around 3 hours with the temperature of 700 degrees Celsius. Okay, so these are the results for particle size distribution by using laser particle analyzer. We can see that the process of high energy milling gradually reducing the size from 1612 nanometer to 419 nanometer in size for nanokaolin, and after calcination, the size from 419 nanometer reducing to 176 nanometer that been used and that been claimed as the final size for nanometakaolin by using high energy milling. Okay, the best thing of this new kind of nanomaterial producing in ISEM lab is the size, the increase of size, uh, the size of the mean size of that particular nanometakaolin been reduced up to 1,000, less than 1,000 nanometer, and the surface area increased from 27,000, almost 27,000 meters squared per kilogram to 140,000 meters squared per kilogram, which can become a very good ultra filling effect in the cement paste. Okay, for nanoclay, there is no process involved regarding nanoclay because nanoclay being provided by Sigma Aldrich, and the idea to include nanoclay in this particular research is to see the difference between local material produced in Malaysia, which is nanometakaolin, to compare to nanoclay, which is already known in the European countries for clay-based advanced materials. So as we can see here, there is not so much different in terms of effective site of nano based on calcination process. So nanometaclay recorded 146 nanometer in size after calcination. Okay. Right. So these are the elementary analysis by using SRF or to detect the what kind of element or minerals uh, uh, in the structure of that particular cement, kaolin, metakaolin, nanokaolin, and nanometakaolin, and also nanoclay. So we are for cement practice, we focus more on the SiO2 and Al2O3, which is silica oxide, and Al2O3 due to the element of SiO2 is to enhance the performance in terms of strength properties, and for Al2O3 is to enhance to to improve on the water demand and also the setting time of the cement paste from liquid to solid. Okay. Others is minor material to be included, for example, CaO, calcium, titanium oxide, ferrum, and also kaolin. Okay. So as we can see that the differences between the element of SiO2 from metakaolin to nanometakaolin increase around 10% of silica after the calcination process. So from this, we can see that the calcination process partly enhance or play a major role in producing or reactive the process of silica that automatically will enhance the bonding effect of the cement paste itself. Okay. Next, to confirm on that particular elementary analysis, we done the test on the composition effect by using SRD, and as we can see here, this is for the data tabulated by SRD on the elementary process from kaolin, metakaolin, nanokaolin, and also nanometakaolin. And on the right of the screen, this represent on the nanoclay from nanoclay to nanometaclay. So as we can see from this SRD peak, we can see that the process transformation from microparticles, which is kaolin and metakaolin, into nanoparticles, which is nanokaolin and nanometakaolin, that regards with the inclusion of calcination process also improve the element of silica, which is the SiO2 peak around 27 to 28 2 theta is more than 10,000 as compared to kaolin around 4,000 to 6,000. Okay, so there is a double process increment of silica oxide due to the calcination itself. On contrary, on the left, on the right of the screen, this is the process on the transforming nanoclay into nanometaclay. So we can see that the element of the red line represent the nanoclay, which is not involving on the treatment process, which is calcination. So after calcine, we can see the peak of that particular nanometaclay, the peak and the noise of that particular blue line is stable as compared to nanoclay. Means that due to the process of calcination, it makes the nanometaclay more stable, and when it paired with cement in the cement paste during the process of mixing, it can produce a very good binder. Okay. So these are the SEM image on that particular OPC, kaolin, and also metakaolin. So this one, A is OPC cement. We can see what we call as angular and rough particles. So this one is kaolin. Kaolin we can claim, already been claimed by previous researchers as flaky, elongated, and platy. Okay. And the structure of flaky, elongated, and platy for metakaolin remain, only the flakes break into pieces after the calcination process. So this is from these figures, from these SCM images, we can see that the calcination process increase the surface area of that particular material. So, so from this we can conclude that the process of filling effect, the ability of metakaolin to become a very good filling effect in the cement paste or concrete is very good. Right, so this one is the process of transformation from nanokaolin to nanometakaolin, and nanoclay from to nanometaclay. So on this left side of this screen shows on the pack component of nanokaolin after milling process. But again, as I stated earlier, nanokaolin is not reactive. Okay, so we need to process of what we call as calcination to transform that particular silica oxide into this kind of images that we call as nanometakaolin. So the flakes of flaky elongated pieces is break into what we call a single flake compared to crowded flakes. So these single plate flakes elements represent on the reactivity of that particular nanometakaolin in terms of silica and also alumina. So the same goes to images for SEM in C, which is represented by nanoclay. A unique image of nanoclay been captured by SEM, which is what we call as a rounded shape element. Okay, and after the process of calcination, we can see that that particular rounded shape is break into smaller particles of rounded shaped element, which prove on the enhance in the increase on the surface area that been discussed earlier in the PSD results. Okay, right. So these are the setting time and water demand. It's very clear. Nanometakaolin and nanometaclay as addition increase the water demand of cement paste. This can be expected due to the pack component of cement with the inclusion of nanometakaolin and nanometaclay without the element of replacing. Okay. So for replacement element, the demand of that particular setting, the water demand for the cement to achieve a standard consistency is less as compared to the addition method. This happened due to the element of replacement of cement in the replacement method. Okay, right. So this data, the final figures representing on the compressive strength of cement paste from day 3, 7, and 28. So A is represented by addition method and B is represented by replacement method. So we can see a very different style of strength development compared to the addition and replacement method. For example, at day 3, we compare to addition for day 3 to replacement method at day 3 for replacement. We can see that for replacement, the effect of nanomaterial, which is performed by nanometakaolin and nanometaclay, uh, achieve around 85 MPa at day 3 for nanometakaolin itself. So we can see that we can the element of nanometakaolin in the cement paste increase what we call as early strength effect. Okay, so basically in the industry, the element of these particular findings can be used as a good repair materials similar to the grouting effect that been used in the industry right now. So at day 7 again, the replacement material, the replacement technique of nanomaterial, which include of nanometakaolin and also nanometaclay, perform gradually and increase the strength as compared to the grade 3. Okay. So for addition, what we can what can I conclude from addition is the inclusion of nanomaterial in this particular method perform very late strength effect. Okay, the strength only occurs obviously at day 28. And again, for replacement method, the strength achieved by nanometakaolin and also nanometaclay is almost the same, which is 120 MPa in strength. Okay, so this what can I conclude from this particular findings is the reason of replacement method to achieve very early strength is due to the ultra filling effect from the finer particles of nanometakaolin and nanometaclay, which increase the surface area of that particular cement paste as compared to addition. In addition, the results of the slow setting of that particular cement paste is due to the compactness of nanomaterials with the inclusion of no replacement of cement, means that that particular design for addition method, there is no space between the cement paste and the in the cement paste itself, and the reaction of nanometakaolin, either metakaolin or metaclay, is low due to there is no void for them for this particular reaction to create the hydration process. So these are the conclusion that can be made from this particular finding. Okay, these are some of the publications regarding on this particular research, and with that, I conclude my presentation on this particular meeting. Anything regarding on the research for UHPC and also nanomaterial itself in the processing or production method, feel free to email. And that, thank you very much.